All right, so we were talking about maximum margin classifiers the other day, and we got started on it, right? So this is the form of a linear classifier that we have seen before as well. This looks very much like how perceptron was, except in perceptron, we assume that the bias term is already folded in to your x, right? But for support vector machines, we are going to keep it explicit, which means that x is just your d features, and the bias term, the weight corresponding to the bias term is actually b, right? This is just so that it's easier to explain it, right? All right. So what is the role of a or a linear classifier, or the goal of a linear classifier is to learn these weights, right? And we have seen before that geometrically, this kind of means that this is an equation of a line. So basically, you're trying to learn a line that distinguishes between two types of points, right? And we talked about this last time, that with perceptrons, it doesn't care where the line is as long as it goes through the middle, right? As long as it is able to separate the two types of classes. However, it turns out that there is a reason that we might want a line that goes straight in the middle, right? And geometrically I'll explain that reason very soon. But in general, the idea is that you can learn any line which will give you a zero training error, but even after that, the location of the line is important, all right? And that is what support vector machines sort of exploit, all right? So what is the best boundary is the question, all right? So let's first try to understand lines and everything, right, in a geometric fashion, right? So let's say your data is in two dimensions, d is 2, so x1 and x2, right? So when you have a line, essentially what this line is doing is it's dividing your space into two parts, right? So the role of any line or a hyperplane in larger dimensions is to separate your data, or separate your space, this coordinate space, into two half spaces, right? And then the idea is that one type of points will belong to one half space, and other type of points will belong to other half space, right? Now you must have, in geometry in high school or college, you would have looked at lines, right? So typically we express lines as this. Okay, so y equal to mx plus c. That's one way to express a line, right? So I'm going to not write y because y is something else, but let's say we have two attributes, x2 and x1. So typically we write it as x2 equal to mx1 plus c, if you remember, right? So let's say this is x1, this is x2, right? Then this line essentially means that this m controls the slope of this line, right? And this c is this in sort of the intercept on the y-axis or x2 axis, right? However, you can also express the equation of the line like this: w1 x1 plus w2 x2 equal to or plus b equal to 0. So this is also a valid equation of a line, all right? And of course then you can rearrange terms, and you can see that the you can actually say x2 is minus w1 over w2 x1 minus b over w1, right? So which means that this is the slope and this is the intercept. So that's just, or negative of that is the intercept. So that is just an equivalence between these two representations. But for us, we are going to represent the line like this, or we are going to write it like this: w transpose x plus b equal to 0, where where w is a weight vector. So this is a vector which contains w1 and w2. X is a vector which contains x1 and x2, and b is here the bias term. All right. So we are going to express lines like this, which means that this w, right? This w has a special meaning. So okay, let me draw another line, easier to explain. So let's say the line looks like this. So if the equation of this line is w transpose x plus b, then if you go back and do your geometry right, this a unit vector that is perpendicular to this line is given by this. So this is nothing but W, where W is like a vector, right? So if you have a vector, you can represent it as a like this, right? Divided by the norm of W, right? And so this is a unit vector, right? So this is what W represents, and the distance between the origin and this is given by, right? So this is sort of how geometrically we would interpret this line, right? Which means that if you did not have B, this part would be 0. That means that line would have gone through the origin. But we have seen this before, that we want to learn lines that do not necessarily go through origin, because your data might be somewhere else, right? So that's why we introduce this extra term B, so that your line can be placed anywhere. Okay? So then what we do is, to use it as a classifier, essentially we test something, right? So for a new point, if for a new point x star, right? If W transpose x star plus B equal to 0, what does that mean? That point is on the line because it's satisfying this equation, right? So x star is on the line. If W transpose x star plus B is greater than 0, then it's on above the line, or typically we say it's in the same direction as this unit vector, so it's on this side. So x star is above the line. And same way, if W transpose x star plus B is less than 0, then x star is below the line, right? So now if you know the line, you have essentially a classifier, because now you can take a point, compute this, and if it is whichever direction, then the sign of this value, right, will tell you with what class it is, right? So the sign is important. However, as I said earlier, right, this term, this actual value, so for classification, sign of W transpose x star plus B is what we want, right? What we need, right? As long as we get this. So it doesn't matter. So if for certain x star, this value is 0.00001, and for another x star, this value is 10, for both of them, you will call it a positive point because it's on the other side of the line. But this is useful in some way because this tells you how confident you are in the prediction, right? So if there is a point that is right here, which is probably the one for which this value is 0.0001, and there's a, let's call it A, and there is a line point right here, B, you can see that when you get these values, you would sort of know that, okay, A, we are less confident about A being positive than B, right? Which means that the magnitude has some value, right? You want the magnitudes to be large, which means that you want to, so that kind of motivates us to learn lines such that all the positive points are as far as possible, and all the negative points are also as far as possible. So that would give you high confidence predictions, right? So that is the motivation behind margin, right? We want to learn a line such that it is far from all the points. You don't want any point to be close to it, right? So that sort of is the motivation. So we want the magnitude or the absolute value to be large, right? We can also say that if you also know the label of this point, we can say that we want y star times to be large, right? So why did I do this is because if it is a positive point, this value will be +1, right? Then you want this value to be large. If this is a negative point, then this value will be negative. Then you multiply both, it again becomes positive. So in general, for any point, you want this to be large, right? So that motivates, that's a motivation for having maximum margin classifiers, all right? So now we will say how to really quantify the margin, so that then we can write an optimization program to maximize it, right? Now another thing you should always remember is that you do want this to be large, but you also want it to be correct, right? So I mean, for example, if I had if I had a simple data set like this, right, I could have drawn a line far away somewhere here. This will be far from all of them. The margin will be very high. But when you bring this thing in, right, then it ensures that the line should go between them. And then when it is between, then you maximize the margin, right? So that is a given thing, that it has to be correct in terms of classifying the training data. But after that, it needs to be what we want, right? All right. So let's talk about the margin. So when I say a margin, right, the margin is nothing but the distance of a point from this the line, right? So this is the margin, distance of any point to the line. So that is the idea behind the margin, right? So we can geometrically actually compute the margin. So for a positive point, so what is a margin? Right. So for any point, the margin, let's represent it as a what is this term? Gamma. Sorry. Gamma will be W transpose X plus B. So for a positive point over the magnitude of W. Now why will this be? We'll look at it quickly. So let's say this is our line, right? And this, of course, this is that unit vector W. And let's say consider any point here on the positive side of the line, which is this. Let's call it X, right? So consider this projection of X on the line, X prime, right? So this vector is X, of course, right? And this vector is X prime, right? And let's call this R. All right. So you can write R in the geometric sense as X minus X prime. Right. That's simple. Now X prime lies on the line, right? Which means for X prime, W transpose X prime plus B will be equal to 0, right? So I'm going to let's see. I don't want to confuse you. New terms. Right. Now what is R, right? So R is a vector which is perpendicular to this line, which means that R is parallel to this, right? Because this is a vector, this is perpendicular, right? And we are assuming let magnitude of R be that margin, right? Because we are interested in this margin. So which means that R is nothing but this times this, right? And this is nothing but gamma, the actual vector divided by its magnitude, right? Because that's the unit vector along that, right? So that is that. Then we can say that X prime from here, X prime is X minus R, which is equal to X minus, right? And then what I'm going to do is replace X prime here with this value. So W transpose X minus this plus B is equal to 0. So this is coming from here, right? So I'm going to open it, W transpose X minus gamma W transpose W. I'm being a little inconsistent with my arrows, but whenever there's an arrow, it means it's a vector, right? A plus b is equal to 0, right? So just the sidebar, what is this, right? So this is W transpose W. So W transpose W is nothing but the magnitude square, right? So which means that this value will just be the magnitude of W. So W transpose X minus gamma magnitude of W. So by magnitude, just so that you remember, for a two-dimensional W, it will be W1 square plus W2 square, right? That's a norm. That's how we write the two norm. So this is this plus b is equal to 0, implies that I'm going to rearrange. So that means this gamma is nothing but W transpose X plus b over this, right? That's what I said earlier. But this is only for points that are on this side of the plane. But if X is below W, or is below the line, not W, then this will actually be minus of this. That you can work out. Simple, right? So in general, if we know the true label of this point, in general, the margin for any point will be times y, because y will be either plus 1 if it is on above line and minus 1 if it is below, right? So that is clear. Any questions about this? So what I've done so far is just sort of geometrically shown you what the margin means, right? Now, the role of the support vector machine, what we want is to maximize these margins, right? Now, of course, you can compute the margin for every training data point, but you cannot really maximize everything. So what you do is you try to maximize the margin with respect to the closest points to your line, right? So if your training data looks like this, plus 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 and some minus, so whatever line you draw, right, you consider the points that are closest to it and you try to maximize that much. All right, so that is the idea. Any questions so far? Yeah. Well, I mean, see, ideally you want all these margins to be as large as possible, but if you can maximize this, then these automatically will get maximized, right? Because they are farther than this point. I mean, so what these points, right? These are guaranteed to be the ones that are closest to your line, right? So if these are maximized, if you have ensured that these distances are the farthest away from the line, then all of these automatically, since they are all greater than this, right? So they will also be the farthest away that could be. Well, I mean, yeah. So don't think of it as these points being fixed. Whatever these points are. So when you draw the line, there will be some points which are the closest, and you want to make sure that they are farthest from that. So there could be somewhere else as well. You're right. So when you move it, maybe there are some other points which are closest. But in general, this is just an illustration, is that you want that to be the farthest. Okay. So now let's go back here. So this is what I said, right? So you want your margins, of course you want your margins to be positive, right? Because your margin, if the margin is not positive, actually what will happen is that means it's incorrect, right? So margin should always be positive because you're multiplying it with the sign of the label, right? Now this is geometrically how it looks. So let's say you're trying to distinguish between these two types of points, right? So you want to draw a line. When you draw a line, what will happen is that this, let's say this is the line, right? So you can put it right in the middle of the closest 2 points, so it will be symmetric, right? The equation of the line that's parallel to your desired line but goes through the closest point, that equation will be wx plus b equal to 1, and the line that goes through the closest negative point will be wx plus b equal to minus 1. All right, now where does this 1 come from? So actually it could be anything, right? But the thing is that if you look at the equation of this line, right, one thing that I did not mention earlier is this. So if this is the equation of your line, right, which means that 2 times w transpose x plus 2b equal to 0 is also the same line, right? Any cwt transpose x plus cb equal to 0 is also the line, right? So you can multiply it with anything and get that. So that is why what happens here is that when we basically we divide it and such that the equation of the line is this constant is 1. So whatever the value is, you can move all of that there. So this is what you want. You want to learn a line, right, such that now the margin, if you calculate this margin, right, it will be 2 over w. So we can actually easily see that. So let's say this is, I'm just repeating the same diagram here. So let's say these are all my positive points, and these are all my negative points, and this is the line that I want to draw. That means that the margin lines are these, right? I mean they're equal distance, of course. So as we said, this equation of this line is w transpose x plus b equal to 0, where x is basically a vector, and this will be w transpose x plus b is equal to minus 1, and this is w transpose x plus b equal to plus 1, right? So this is the margin that we want to maximize, the total margin, right? So this margin, what I'm saying is, will be equal to, the margin will be 2 over magnitude of this w. How will that be? We can look at that. Right. So basically for these points, right, if you remember, the gamma is nothing but for the positive points. Gamma is this, right? Gamma is w transpose x plus b over magnitude of w for positive points, right? But if they are on the margin, that means that this value is 1, right? So for positive points on margin, this gamma will be 1 over this, right? And then the same way for negative points on margin, this gamma will again be 1 over this, right? Because for the negative point, the margin is minus of this. Where did I have that? The margin is negative, right? So, and then this one will be minus 1, so it will still be plus 1. So which means that total margin is equal to 2 over 3. All right, so this is what we want to maximize. So what we have done so far is we have quantified the value of the margin that you want to optimize on. All right, any questions so far? Okay, so moving on. Now how do we do that, right? So we have given, we have some data set, right? Of course, so that one algorithm that does that is support vector machines. So it is essentially a hyperplane based classifier, which is basically a linear classifier, which has two sets of parameters. One is this weight vector w and weight vector w and the bias term b, right? So it is kind of exactly like logistic regression and like perceptron, right? Except that in perceptron and logistic regression, we assume that b is inside w also, but in this term it is like this. But the prediction rule looks like this, all right? The prediction rule is you're checking the sign of this value. If it is greater than 0, call it positive classifier or positive point. If it is less than 0, call it negative point, right? So it is kind of like perceptron. Now you can see the differences with let's say logistic regression, right? So logistic regression, the rule is slightly different. In logistic regression, we compute the sigmoid of this value, right? And if it is greater than 0.5, you call it positive, otherwise negative. In the case of perceptron, I guess we are doing the same thing here, like this, right? So now you're given some training data like before. You have n data points, you have their values, x's, and the predictions or the labels, y's, and y's can just be +1 and -1. And you are trying to find the hyperplane which maximizes the margin, all right? Plus, it also divides the data. Of course, that is a given, right? Now here we are going to assume that the data is linearly separable. That means you can draw a line, which is like this, right? Later on, we will see a case where, the real benefit of any classifier is in the case where your inductive bias doesn't hold, right? Which means that data is not separable. So we'll talk about it later, but today we are going to assume that it is linearly separable. So now we want to learn W and B that maximize the margin as well as have the zero training error. So we will see how to express it as a optimization function. So this is the optimization function for linear regression or for support vector machines. Now remember, we were trying to maximize this margin, right, which is 2 over W. So what I did was I flipped it over. So if I'm trying to maximize this, it is same as trying to minimize this, right? Because then it's easier to differentiate and everything, right? So we flipped it over. So we want to find those parameters which minimize this margin, but they also ensure that the data is correctly labeled, right? So these constraints ensure that your data is correctly classified, your training data, right? Because this quantity will be greater than equal to 1 only if all the points are on the right side of your line, and this ensures that your margin is maximized, right? So this is the point where things start looking different than perceptrons or even neural networks or logistic regression. There we were trying to basically maximize this, or you were trying to minimize something that was working on your error, right? But here you're assuming you're putting these things as constraints. So this is slightly different than the optimization functions or formulations that you have seen earlier. Earlier we were looking at what we call unconstrained optimization. You just had a objective function over here and then you're trying to find the value, but here it is what we call a constrained optimization. So it's optimization with n linear inequality constraints, right? So because if we didn't have these constraints, right, then the value would just be 0, because for W all weights to be 0, that will be the right answer, but that would not be the correct answer, of course. So you want to have these. So now what we will do is so of course now we cannot do direct gradient descent here, right, because gradient descent does not ensure these constraints. So we will look at how to solve these, right? If you're familiar with optimization and different methods in optimization, and if you're familiar with something called linear programming, right? So linear programming works if you have an optimization equation formulation in which you have many linear constraints. So these all constraints are linear. Why are they linear? Because they are basically all your parameters, these W's, they are all there as a linear value, right? There is no square of W or square of B or cube of B. But in linear programming, you assume that even your objective function is also linear in W. So of course, linear programming won't work here. W is the objective function is quadratic in W here. So quadratic programming is what you need, right? So of course, and then we'll see what it is. So let me just talk about margin again. So we've talked about maximizing this margin, right? So what does large margin mean? Because we are looking at this, right? So maximizing the margin means we are trying to minimize your W, right? So we are trying to minimize this squared value of W. So the real good answer would have small values, right? Now we have already seen this in linear regression and neural networks as well, is that we do regularization to control this, right? Remember in your linear regression, ridge regression, we always had this regularizer term, lambda w transpose w by 2, which is same as this, right? This is just w transpose w square root of that, right? So which means that we are kind of, by doing this maximization of margin, we are actually regularizing our solution, right? We are trying to go to the simpler solution, which means going through the logic of following the logic of having simpler solutions, this would have better generalizability, which follows the Occam's razor principle. And if you read up more theory on this in the sort of literature on computational learning theory, you will see formal justification of this. So there's an excellent book by Vladimir Wapnick, right, who sort of invented support vector machines. But he has a book called Statistical Learning Theory, right? That sort of sketches all of this out. So if you're interested, you can look at it. But today we are just going to assume that because of this connection, right, by maximizing the margin, we are trying to go towards better generalizability as well, right? And later we'll also see things like, using kernel methods and everything. So there, when you do polynomial expansions and basis function expansions, having small w, we have seen that before, also has an effect of keeping the solution simpler, right? So that sort of is another motivation for doing maximum margin, right? Any questions so far? All right. So moving on. So now we have to solve this optimization problem, right? As I said, it's a quadratic objective function because you have to optimize over w with n linear inequality constraints, right? So we haven't seen any method so far to solve this. However, there are a lot of solutions, right? So if you, in MATLAB, there's a program called quadprog. In C, there's convex optimization package. I'm sure there's something in Python as well. You can just, supply these weights and, initial values of these weights, supply all of these inequality constraints and solve for it, right? And so we could be done here, right? So I've shown you what a support vector machine is, and then we know what is its prediction rule, right? And what I've shown you here is that you can come up with a solution that, so you can use these programs and optimize for this. But it turns out that this is not the best way for support vector machines, and there are several reasons. One of the reasons is that there are too many constraints here, right? The n constraints, and they grow with your data. Yeah, that is one. And then later on we will see that this, if you want to apply kernel, the kernel trick here, right? It won't work here, because you are trying to do W transpose X. That means you're assuming that your X is a d-dimensional vector. So if you want to apply support vector machines to non-vector data, right? Or if you want to do things like projecting things to infinite space and bringing it back, you can't do that with this formulation, all right? So that is why there's another way to explore it. So we are going to do that today and on Monday. Okay, so to do that, I'm just first going to give you a basic introduction of how to solve these optimization problems with constraints, right? And I won't go into too much detail, that's not our focus. So, but if you pick up any math book on optimization, these things would be there, right? So let's say this is our problem. We have a function that we want to optimize on. We are trying to minimize the function, and we want to find the x and y that minimizes this function, right? So let's say this is the function. Now, if that's the only part that is there, then you know how to do that, right? You can set the gradient, you compute the gradient, set it to 0, right? In this case, it will be 2x minus 4y. Set it to 0 and compute your x and y. Or you can do gradient descent or whatnot, right? So you can do that. But what if I add some constraint, right? So I have this objective function, but I also have constraint, which means that the solution that I get should follow this. So it means that x plus y should sum up to 1, which means that if I directly optimize this, they might not satisfy this constraint, right? So that is sort of the idea behind constrained optimization problems, right? So let's say you only had one parameter x, and this is your fx, right? And let's say you're trying to optimize over it, right? Of course, this is easy to do. You just find the derivative, set it to 0, you'll get this point, right? But let's say you have set some constraints. The constraints say that x can only be less than this or greater than this. Then this solution is not correct because it does not satisfy the constraint. So now what you want is you want to find the solution which is valid here. So you want to find the maximum in this region and in this region, right? So that is the idea, that is the issue with that. But you don't have to worry, there are mathematical formulations to solve it, and we're going to look at one of them, right? So there is one method called the method of Lagrangian multipliers, right? So what that lets you do is basically you're solving this constrained optimization problems of differentiable functions, of course, which means that this function needs to be differentiable. So there are some constraints. What you typically do is you for every constraint, right, you add a Lagrangian multiplier. So this is a scalar alpha, right? And what it lets you do is you multiply this with your constraint and you bring it into the main function. So now you have converted this constrained optimization problem into an unconstrained optimization problem by introducing an additional variable, additional parameter that you want to figure out now. So now you want to minimize this function and find the x, y, and alpha that minimizes that, right? And what will happen is that whatever solution you get, because you're minimizing this, right, it will satisfy this constraint. All right, so that is the idea. So that's the idea behind Lagrange multiplier method. All right, you can also use it for multiple constraints. So let's say you have two constraints, right? You can get two Lagrangian multipliers. If you have n constraints, you get n Lagrangian multipliers, right? But basically, it lets you add them. It also lets you add handle inequality constraints. So in the previous two examples, these were what we call equality constraints, right? I mean, this actually was a very weird constraint. It's saying that x should be -1 and y should be -1. But this is just an illustrative example. But you can also incorporate inequality constraints by putting constraints on alpha. So what happens is, for example, here, what you would do is, here the constraint is inequality constraint. So you add that here. You say minimize x cubed plus y square plus alpha times x square minus 1, subject to alpha being greater than equal to 0. Okay, so it is still a constraint optimization problem, but it is a simpler constraint optimization problem where you're just trying to find those solutions in which alpha is greater than 0. All right, so it's easier to solve. So those are the ways you do that. So what happens with that is that helps us solve our optimization problem for SV. So let's say this is your so again, this is your optimization problem. So first we are going to go through a very simple toy example. Okay, so let's say your x is in two-dimensional space, right? And you have two training data points. One is 1, 1 minus 1, and other is 2, 2 plus 1, right? So one of them is a negative point, one of them is a positive point, and we want to find the best hyperplane which minimizes this, but it's subject to these constraints. So how would you do that, right? So what you would do is you will convert it into these, right? Because you have only two data points. Your n is 2. I will just list those constraints here. So we are trying to minimize this subject to these two constraints, right? And then I'm going to replace the values of x and, because we know what x and y are, right? And then now this becomes a simple. Now what we do is we bring them up. Okay, we bring them up by introducing two Lagrangian multipliers, alpha 1 times this plus alpha 2 times this, and then we solve another constraint optimization problem in which the objective function is different, but here you just have the constraint that all alpha 1 and alpha 2 should be greater than equal to 0, right? What will happen is that this you can manually solve. So if you go home, what you can do is you can actually find the solution for that new equation, and then it would give you multiple answers. Let's see. So you are trying to say minimize W, right? And subject to, the first constraint is that the first data point should be correctly classified, which is actually negative point. So this should be greater than or equal to 0. And the second constraint is that the second data point should be correctly classified. This should be greater than or equal to 0, right? So what you do is you say, now let's minimize W alpha 1 alpha 2, and we come up with a new objective function, which is half W square alpha 1 times G1 x2, right? Alpha 2 G2, right? Subject to right. So what you can do when you go back is you can actually compute this, right? Because this is you can write it as half W1 square plus W2 square if your W is a vector. So W is a vector with W1 W2 and minus, and then you can actually open this up and you'll get a nice equation, right? You can solve it, and what you will see is that you will get multiple possible answers. For some, this constraint will be true, for some it won't be, so you choose the one in which this constraint is true, and then you get W, right? But this is of course a manual way to do it, right? You can do it if you have 2-3 data points, but in practice you will have n data points, n could be anything, right? So how do you solve for that? So what you do is you do the same strategy. So this was your original formulation. You rewrite it as a what we call a primal Lagrangian, and I'll tell you why we have a primal here. But essentially you rewrite it like this. So you have your original objective function, and then you add all of these constraints using these Lagrange multipliers. So because you have n data points, which means you have n constraints, right? Which means that you will have n Lagrange multipliers. So now you have to solve this equation, this objective function, right? So the benefit that you have received here is that you have converted these constraints into simpler constraints. So we can now stop here as well, which is we can say let's just feed this to a convex optimizer, our CVX OPT or MATLAB's solution, and get the right answer. But what we will see next is that you can now solve something more interesting, which will help us more, right? So just to give you because we don't have any more time, what we are going to do in the next class is we are going to formulate we're going to come up with another formulation of this optimization function, which we will call the dual, right? So this is the primal Lagrangian formulation. Then we'll come up with a dual formulation in which instead of minimizing something, we will maximize something else. So it's a common strategy in optimization, quadratic optimization. So instead of solving the primal form, you solve the dual form, and that there you're trying to maximize something. And for nicely behaved functions, what will happen is that what we call is something called a duality gap, where the solution for the primal and the solution for dual, they're going to meet, which means that whatever answer you get by solving for the dual will be the answer solving for the primal, right? But we are going to look at it in more detail next time. Now somebody could ask me, why are we doing that, right? The reason why we do that is because then it will help us use kernel methods with support vector machines. So that will be what we do next time. All right, any questions so far?